Hello everyone, my name is Jovan Komatovic and I am the second year PhD student at EPFL under the supervision of Professor Rachid Guerraoui. Today, I will be talking about the dynamic Byzantine reliable broadcast primitive that generalizes the well-known Byzantine reliable broadcast to a dynamic environment. This is a joint work with my supervisor, Rachid Guerraoui, Petr Kuznetsov from Telecom Paris, Yvonne-Anne Pignolet from DFINITY, Dragos-Adrian Seredinschi from Informal Systems, and Andrei Tonkikh from the National Research University Higher School of Economics. Let me start by presenting the roadmap of today's talk. Firstly, I will explain how we even got to the idea of studying the problem of the dynamic Byzantine reliable broadcast. Here, I will mention a few applications of the reliable broadcast primitive that motivated us to investigate this problem. Then I will briefly cover the well-known Byzantine reliable broadcast primitive that assumes a static system membership. This part of the talk will help us compare the static and the dynamic variant of the problem. The third part of the talk is devoted to introducing the dynamic case of the broadcast primitive. Here, I will introduce the system model and the guarantees we aim to ensure. Then, the protocol overview will be discussed. Namely, I will explain the main ideas and mechanisms behind the implementation of our protocol. Lastly, I will conclude today's talk with a brief summary of our work. The reliable broadcast is a very attractive primitive for two reasons. First, it is a very powerful primitive. It could be used for maintaining caches in cloud services, for example. Moreover, it was recently shown that reliable broadcast could be used for implementing secure, online, Bitcoin-like payments, which was actually an application that inspired this work. Second, it could be implemented in a completely asynchronous manner. Thus, it is a weaker primitive than consensus. Even though the reliable broadcast primitive is a well-studied problem, there exists an aspect of it that was not investigated prior to this work. Namely, previous work on this primitive assumed a static membership of the system. In other words, processes that are members of the broadcast system could not leave it, or processes that are not members could not join the system. However, assuming a static system membership is not realistic for some applications, like payment systems, for example, because we should enable processes to join or leave the system. This represents the main problem investigated in our work. That is, we investigate how to enrich the Byzantine reliable broadcast primitive in a way that allows processes to join or leave the system. Moreover, we still consider a completely asynchronous setting. Thus, we do not rely on the powerful consensus primitive. Our contribution consists of definition of the dynamic Byzantine reliable broadcast. Namely, we generalize the properties of the static Byzantine reliable broadcast primitive to a dynamic environment. Furthermore, we provide an algorithm that implements this problem. And lastly, we show that properties we provide are optimal. Specifically, we show that strictly stronger guarantees could not be ensured in an asynchronous dynamic setting. For the sake of time, I will today cover only the first two contributions. If you're interested in the proof of optimality, please read our paper. Now, I will briefly review the Byzantine reliable broadcast primitive that operates in a static environment. This primitive allows processes to broadcast messages and to deliver messages. Broadcast is an operation that aims to disseminate a message with some guarantees that we will introduce shortly, whereas deliver is a callback trigger to handle a delivery of a message. For example, if the sender invokes the broadcast operation for a message, we expect the receiver to eventually trigger the deliver callback for that same message. However, we need to precisely reason about the properties ensured by the static Byzantine reliable broadcast primitive. Namely, this primitive ensures the validity, consistency, and totality properties. I will now briefly introduce these guarantees. The validity property states the following. If the sender is correct, every correct process delivers its message. So, if the sender broadcasts a message M, then every correct process eventually delivers M. Next, we have the consistency property that simply states that correct processes deliver the same message, even if the sender is malicious and broadcasts two different messages. For example, if the sender is Byzantine and broadcasts messages A and B, all correct processes that deliver a message deliver the same message. In this example, it is the message A. Lastly, we have to mention the totality property. The totality property ensures that if a correct process delivers a message, then every correct process delivers a message. In other words, either all correct processes deliver a message, or no correct process delivers any message. If we combine all three guarantees, we reach that if the sender is correct, every correct process delivers its message. Otherwise, either every correct process delivers the same message, or no correct process delivers any message. Now that we have seen the static reliable broadcast, I will present the dynamic variant. Namely, I will introduce the system model as well as guarantees we provide. Firstly, we assume that there exists a universe of asynchronous processes. Hence, we do not make any assumptions about communication delays or relative speed of the processes. We assume reliable point-to-point communication between correct processes. Namely, if a correct process sends a message to another correct process, that message is eventually received. Processes have access to an asymmetric cryptographic system. Correct processes communicate with only signed messages. Once a correct process receives a message, it can verify its authenticity and use it to prove its origin to other processes. In every execution of our dynamic Byzantine reliable broadcast, only a finite number of processes can join or leave the system. In reality, it is possible to have an infinite number of processes joining and leaving the system as long as the broadcast operation is concurrent with finitely many reconfiguration requests. Namely, it is important in practice that the system remains stable for sufficiently long in order for started operations to finish. We make the assumption that the initial membership of the system is known to all processes from the universe. This is an important assumption that allows processes to determine through which membership the system has gone in an execution. Lastly, we assume a weak broadcast primitive that guarantees that if a correct process broadcasts a message, all correct processes eventually deliver the message. If we assume that the universe is finite, then this broadcast primitive is nothing more than the best effort broadcast. But having a finite universe could seem unnatural in our dynamic setting. Hence, we could assume an underlying gossip protocol that implements this weak broadcast primitive. In this way, it is not required for a correct process to know all the members of the universe. Dynamic Byzantine reliable broadcast offers the following three operations and a callback. DBRB join is invoked once a process wants to join the system. DBRB leave is an operation invoked once a process wants to leave the system. DBRB broadcast is invoked once a process aims to broadcast a message. And lastly, DBRB deliver is a callback triggered to handle a delivery of a broadcast message. Now, I will discuss how processes change their state and when they become a part of the system. All processes start outside the system. We say that these processes are not in the system and they are not currently participating. Here, they can invoke only the DBRB join operation, and once this operation is completed, we say that now they are in the system and also they are participating. Note that we assume that members of the initial membership of the system have invoked and completed the DBRB join operation. Lastly, the DBRB join operation could be invoked at most once. Hence, a process cannot join and then leave the system and then again try to join it. Of course, in practice, this could be easily overcome if a process simply adopts another identifier. Processes that are participating can invoke the DBRB broadcast operation in order to broadcast a message. Also, they can handle the delivery of a message by triggering the DBRB deliver callback. Of course, they could also invoke the DBRB leave operation in order to leave the system. Note that once the DBRB leave operation is invoked, a process is not participating anymore, but it is still in the system. In other words, process has not yet left the system. Again, the DBRB leave operation is invoked at most once by a correct process. Once a process is in the system, but not participating, it can no longer invoke the DBRB broadcast operation. However, it can still handle the delivery of messages via the DBRB deliver callback. Lastly, once the DBRB leave operation is completed, the process goes back to the initial state. Namely, it is not a participant and it is not in the system. Moreover, it cannot invoke the DBRB broadcast nor the DBRB deliver callback. Now, we are ready to present the properties of our dynamic Byzantine reliable broadcast primitive. That is, we introduce the consistency, liveness, validity, and totality properties. Let us start with the consistency property. The consistency property ensures that all correct processes deliver the same message. Note that there are no differences from the matching property in the static case. Then, we introduce the liveness property that simply states that all operations invoked by a correct process eventually complete. Note that this property is implicit in the static case, since a broadcast operation invoked by a correct process eventually completes. We make this guarantee explicit since we want to ensure the same for the DBRB join and DBRB leave operations. Since the validity and totality properties are more complicated, the next few slides will be devoted to these properties. Firstly, we present the validity property. The validity property ensures the following. If a correct process broadcasts a message M at some time t, then every correct process, if it is a participant at time t prime that is greater than or equal to t and never leaves the system, eventually delivers M. In other words, if a message is broadcast at some time t by a correct process, all correct processes that join the system after time t and never leave the system will eventually deliver M. Let us now illustrate this property on a simple example. Suppose that the sender broadcasts a message M at time t equals 4. As you can see, processes 1, 2, and 3 are participants at this time. At time t equals 10, process 4 is also a participant in the system. However, at time t equals 17, process 1 left the system. Note that the validity property does not guarantee that process 1 delivers the message, even though it was a participant at the moment of broadcasting the message. The reason is that process 1 leaves the system. In other words, process 1 is not in the system forever. However, at time t equals infinity, processes 3, 4, and 5 are participants, and these processes are guaranteed to deliver the message. As we have already mentioned, the reason is that these processes remain in the system forever. Lastly, there is a totality property of our dynamic, reliable broadcast primitive that states the following. If a correct process delivers a message M at some time t, then every correct process that is a participant at time t prime that is greater than or equal to t eventually delivers M. Hence, if a correct process delivers a message M, then all correct processes that have not yet expressed their will to leave the system will eventually deliver M. Note that validity ensures that every correct process that remains in the system forever delivers a message, whereas totality ensures that a process that has not yet expressed its will to live by the time of the delivery will deliver the message, even if it does not remain in the system forever. Let me now briefly illustrate the totality property. Suppose that process 1 delivers a message at time t equals 2. The totality property ensures that processes 2 and 3 will also deliver this message. Note the difference from the aforementioned validity property. Namely, the totality property guarantees that processes 2 and 3 will deliver the message even if they leave the system. In other words, these processes do not need to remain in the system forever and will still deliver the message. Hence, at time t equals 10, process 2 delivers the message. Now, at time t equals 23, process 3 delivers the message, even though it has invoked the DBRB leave operation and will leave the system. As I have said, even though the process does not remain in the system forever, the totality property guarantees that it will deliver the message. Lastly, at time t equals 41, process 4 delivers the message. Namely, even though process 4 was not a participant at the time of the first delivery, the totality property ensures that it will deliver the message, even if it does not remain in the system forever. Now, I will give a brief overview of main mechanisms that allow us to implement the dynamic Byzantine reliable broadcast primitive. I will explain how we ensure the consistency property, since the main ideas of our implementation could be seen there. Since our work is inspired by FreeStore protocol that deals with an asynchronous reconfiguration in the crash stop model, some of the abstractions and ideas are similar. However, our work is concerned with more severe Byzantine failure model. Moreover, we investigate the broadcast problem, whereas FreeStore protocol is concerned with the register emulation problem. First, we consider a set of changes that represents the Cartesian product of a set that consists of plus and minus symbols and a set of process identifiers. For example, an ordered pair plus P signalizes that the process P wants to join, whereas an ordered pair minus P signalizes that the process P wants to leave. Then, we introduce an abstraction of a view. View is a set of changes. For example, this represents a view. We can define the set of members of a view. A process P is a member of a view if an ordered pair plus P is in the view and an ordered pair minus P is not in the view. In this example, processes Q, R, and S are members of the view, whereas process P is not. Moreover, each view is equipped with a quorum system, a collection of subsets of members of the view. In our protocol, quorums are all subset of members of the view that consist of 2/3 of all the members. We make the following standard assumption. Every two quorums have at least one correct process in common, and there exists at least one quorum that contains only correct processes. When we talk about relations between views, two views could either be comparable or conflicting. Two views are comparable if one is a subset of another. If that is not the case, then the views conflict. But why do we even need the abstraction of a view? Well, since we cannot solve the consensus problem in an asynchronous setting, it is impossible to ensure that all processes have the same knowledge of a system membership. That is why we introduce views. Namely, a view represents a membership of the system through lenses of a certain process. Let me explain briefly how the system evolves. In other words, let me show how the fact that processes want to join or leave the system is reflected in our protocol. The evolution of a system is reflected in the fact that new views are instantiated by our protocol. Let us take a look at an example. Suppose that the initial membership of the system is reflected in a view 1. Here, processes P, Q, R, and S are members of the view. Suppose now that some process Z wants to join the system. This is reflected in a new view, view 2, that builds on top of the view 1 with the addition of an ordered pair plus Z. If now process S wants to leave, the view 3 reflects this change. Note that the view 3 consists of both plus and minus S ordered pairs. The invariant our implementation ensures is that all of these views are comparable. This is the consequence of the fact that new views are built on top of old views, thus ensuring the comparability invariant. As I have already mentioned, the consensus problem cannot be solved in an asynchronous system. But what does that really mean in our context? The previous slide shows that new views emerge as processes want to join or leave the system. Let us present the same example. Hence, we have the view 1, which represents the initial system membership. Remember that the view 1 is known to all processes. Since process Z wants to join the system and process S wants to leave it, we could end up with two new views, view 2 and view 3. The fact that agreement cannot be reached prevents us from creating a protocol where all processes will consider the view 2 as a system membership after the view 1. Similarly, we cannot ensure that all processes consider the view 3 as a system membership after the view 2. In summary, we cannot ensure that there is a single successor for a given view. In other words, something like this could happen. Namely, some process might consider the view 3 to be a successor of the view 1, whereas other processes might consider the view 2 to be a successor of the view 1. In this scenario, the view 2 might be skipped by some processes. In our protocol, there is a notion of installed views. These views are more important than non-installed views, as I will show in the next slide. One of the most important features of installed views is that they cannot be skipped. In other words, all processes will be aware of these views. They might not be aware of the fact that these views are installed, but our protocol ensures that these views cannot be ignored by any correct process. I will now briefly explain how we ensure the consistency property. This illustration will nicely present the main intuition behind our protocol. Firstly, let me briefly restate the consistency property. The consistency property states that all correct processes deliver the same message. As we have discussed in previous 2 slides, installed views cannot be skipped and are totally ordered. We could take a look at an example with 4 installed views. Remember that between views presented in this example, there might be other but non-installed views. Before a correct process delivers a message, the process checks whether the message is equipped with a message certificate. Message certificate represents a set of acknowledgements for the message, given by a quorum of some installed view. Hence, if the faulty sender wants to violate the consistency property, it needs to collect message certificates for at least 2 different messages. Now, let the view 2 be the oldest installed view in which a message certificate is collected, and let that message certificate be for some message M. We must show that the faulty sender could not collect a message certificate for some other message M prime. Since correct processes only acknowledge 1 message per view, it is easy to see that the faulty sender could not collect a message certificate for M prime in the view 2. But what about subsequent views? Once a correct process starts considering the view 3 as the system membership, it is aware of the view 2 and waits to receive information about acknowledged messages in the view 2 from a quorum. Because of the quorum intersection, all the correct members of the view 3 will learn that message M was acknowledged in the view 2. Importantly, once correct members of the view 2 send this information, they stop acknowledging any messages in the view 2. Lastly, if a correct member of the view 3 learns that the message M is acknowledged in the view 2, the process will acknowledge only the message M and no other message broadcast by the sender. The same scenario occurs at the view 4. Namely, the correct members of the view 4 will acknowledge only the message M and no other message. Hence, if the sender collects a message certificate for some message M prime, then M prime is equal to M. We use the similar ideas in ensuring the validity, totality, and liveness properties. For more details, please take a look at our paper. In summary, we have studied the dynamic case of the reliable broadcast primitive. Namely, we enriched this primitive by allowing processes to join or leave. We have considered completely asynchronous environment. Hence, we were not able to use the powerful consensus primitive in solving the problem. We have defined the guarantees provided by the dynamic Byzantine reliable broadcast primitive. Moreover, we have devised a protocol that implements this primitive. Lastly, we have showed that guarantees we ensure are optimal in a dynamic asynchronous setting. Let me conclude today's talk with an invitation to read our paper. Thank you for your attention.